Greetings. Again, this is Dr. Truitzen. I will be talking about Chapter 1 today. In the text, which again, this is the textbook that I will be using for the course. It's the 7th edition. The 6th edition is perfectly okay. You do not have to have your own copy of the text. It's possible you might be sufficient just by using the PowerPoint lectures I have on D2L in regards to the text. A couple other notes here. I'll be saying I will start Zoom classroom meetings the week of August 31st. This week I'll just be posting videos related to the class as far as each chapter is concerned. Again, the length of these will be no more than about 15 minutes. And then I will be answering questions on email. There will be no specific problems from the textbook, but I'll be doing some examples from the text as far as that's concerned. So don't panic about getting the text, or if you want to borrow one or you can buy one somewhere. I don't have it in the bookstore because it's a very expensive book and it's not always necessary to have it. So try it with what we have in the materials on D2L. There's no access code required, and that's how it's going to be. The labs, again, will be entirely online this semester, with the possibility of maybe having some in-class ones as far as that's concerned. As far as meeting with me, you can do that in person, again, by request in room 310, starting next week if you have questions. So I'll be posting the time frame up as far as that's concerned. And again, all the assignments are quizzes for submission. Check the due dates for them, check when they open, check when they close, as far as that's concerned. So if you have any questions, I'll be sending out a mass email to everybody in class today as far as how the class is going to go. So this is on Chapter 1. Chapter 1 is on measurement. All right, and the first question that brings up in the book are 1 cubic meter equals how many cubic centimeters? All right, now we know that 1 meter is 100 centimeters, right? The cent is 100th. We'll get into prefixes later. But remember, this is volume. Dimensions of cubic are volume. Dimensions of square are area. So a volume of cubic meter is going to be 100 by 100 by 100. So 1 cubic meter will be 100 centimeters by 100 centimeters by 100 centimeters is 10 to the 6th centimeters. Again, in power of 10 notation, scientific notation. So that's how that's going to be. While we're on that, we'll talk about units. All right, we are going to be using the MKS system. Meter, kilogram, second. All right. Now, I may be using some conversions along the way as far as that, but the purpose of using English units is only so that you can get a sense of what they really mean. So if we talk about a distance, what does that really mean? All right. So, units of prefix. All right, so jumping around here a little bit, we have 1 meter, And this will be true whether it's meters, kilograms, second. Kilogram, so we have going is 10 to the 0 meters, so that's 10 to the 0 is 1. We go smaller, 1 centimeter is 10 to the minus second meters. 1 millimeter is 10 to the minus third meters. 1 micron, the Greek letter mu, is 10 to the minus sixth meters. 1 nanometer is 10 to the minus ninth meters. And it's probably the smallest we'll use, 1 picometer. P is 10 to the minus 12th meters. All right? Going upwards then, well, the first one we normally use, there aren't any really in between, but we have a kilometer is 10 to the third meters. Megameter is 10 to the sixth. Gigameter is 10 to the ninth. Terameter is 10 to the 12th. And if you really want to get bigger, it's petameter. We use this with petabytes, terabytes, gigabytes, megabytes, is 10 to the 15th meters. Now the video that we'll be showing and taking the quiz with that is the video powers of 10. And we'll be showing that video is on the main link on the content page, and there's a quiz associated with that along with the questions. So again, you can ask me questions related to this as far as that. So with the powers greater than 1, they're all capital letters. With the smaller, less than 1, they're all small letters. Okay. All right. And, okay. So, related to that, all right, using that, we then have what we'll call significant figures. Significant figures. And the concept of this comes about from the idea of how accurate is a measurement. To give you an idea, if you're in this classroom I'm in, is approximately 10 meters by 10 meters. All right? About, I would guess, it's about 30 feet by 30 feet. If I was to just estimate the size of the room, that would be good enough. So that would be 100 meters squared, right? Okay, now suppose I wanted to be much more precise because, say, I was laying carpeting or precise tile or putting ceiling tiles in somewhere and need to be more precise, all right? In that case, I might need to be accurate to a tenth to a nearest centimeter, maybe even 1/10 of a centimeter. A centimeter is about half an inch, so maybe a 1/10 of a centimeter, 1/1000th of a meter. So say I measure the room and it's 9.93 meters times 9.10.013 meters. If I multiply those two numbers, I will get some number approximately, don't have my calculator with me. I get, let's see, 100.01345 meters squared using a calculator. Now, how is this reasonable? All right, so what do we define by significant figures? How accurate? This one has one significant figure. This number has one significant figure. This number has 4 significant figures, and this one has 4 or 5. So our answer, even though this has actually 1, 2, 3, 4, 5, 6, 7, 8, because that's what the calculator might generate, thereabouts. I don't need to calculate exactly. Our answer can only have one significant figure. And actually, it's going to be 1, 1. 5 significant figures at most. So when these numbers are irrelevant, and this would be my 100 point, not even multiply right. So 100.11 meters squared. That would be the accurate. That would be the area of this room to the nearest 5 significant figures. So that would be the accuracy of the room. Now, in this case, we measured both of them precisely. But what happens if I get sloppy? I measure the first dimension, say the width of this room, accurately to 9.93 meters. But I get lazy and say, well, it's about 10 meters that way, right? 10 meters, and I just sort of wing it. If I multiply these together, I get 99.93 meters squared. Is that correct? Well, this number has 4 significant figures. This one has 1, and this has 4, but when you do a multiplication, the answer is only as accurate as your weakest measurement. This one only has 1. So I can only do this to one significant figure, and that'd be approximately 100 meters squared, which is what this number is. Zeros do not mean anything, they're just placeholders. And that's the example here. So if I have 100, let's say 1,000, this is one significant figure. 1,000.0, this is actually 5 significant figures. And likewise for smaller numbers, 0.0003 meters, this is 1. But if I have 0.000365, this is 3. And if I actually had a 1 in front, 1.0, which is a different number, this would be 1, 2, 3, 4, 5, 6, 7 significant figures. 7 significant figures. So that's how significant figures come about, and that's how we're going to be using them for the rest of this course. So when we do some of the lab measurements, particularly in chemistry or biology, significant figures are extremely important, right? Because if you're trying to measure something, like for analysis, right, you can't just sort of do it like a cookbook recipe. You know, you could throw in a couple eggs, a cup of flour. You may need to use a precise amount of a certain chemical. Certain reactions might work precisely. Biological experiments that way. Physics is the same thing. Engineering is the same way. What precision do you need? And that is reflected in the amount of significant figures in there. Another way to make this a little easier is, say we have this number 3.000368. To change this to scientific notation, we would move the decimal 1, 2, 3, 4. That would then become 3.68 times 10 to the minus 4th. This would mean there are 3 significant figures and such. So when you change it to scientific notation, the significant figures are right immediately obvious there. And here it's not quite obvious, but those zeros are just leading zeros. Much like after here, these are what we call trailing zeros after 1,000. So that's powers of 10 as far as that is concerned. And scientific notation. I'm not going to get into conversions of units for now. I will deal with that when I start talking about chapter 2 in a few days. And we're not going to be doing anything with estimation. That's section 1.7. The other thing we will be using is a little bit of geometry in this class, or trigonometry, I should say. Besides algebra. And what that will mean is that if we have, we're going to be using our Cartesian coordinate system, x-axis, y-axis, and with that, if we have an angle, Greek letter theta, and this is x, y, and this is C, a right angled triangle, 90 degrees, then Pythagorean's theorem, c squared is equal to x squared plus y squared. The hypotenuse, adjacent side, opposite side. As far as this is also concerned, we define the sine of the angle as y over c. We define the cosine of the angle as x over c, and the tangent of the angle is y over x. So opposite over adjacent is tangent, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. So that's a little bit on trigonometry as what we'll be doing as far as chapter 1 is concerned. So that's a brief introduction to chapter 1. You can look at the quiz related to that, the review quiz, which will help. If you have any questions related to those, I'll be glad to talk about those. And again, later on, I will be posting the chapter 2 lecture tomorrow sometime, at least the first part of it. And again, limiting these to about 15 minutes